had a few requests for mass flow rate or volumetric flow rate. I'll explain the difference in a little bit. And it follows on quite neatly from the last video I did about energy and power. And this is sort of crucial basics, I think, for anyone that wants to be a heating engineer. We've got to grasp the very basic concepts of energy and power and the transfer of this energy. So energy, as I said in the last piece, is a potential to do work and is represented as a unit joule. And power is the rate of doing work or the consumption of energy and is represented as a unit watt. 1 watt is 1 joule consumed in 1 second. And as I said before, the critical point of time here, so 1 joule in 2 seconds equals 0.5 watts. Now we're not interested in the kilowatt hour part for this, so we can skip the kilowatt hour part of the first video that we made. Now I want to have a neat look at this second part. So we've got the concept of the joule, and then if we add time, we become watts. And we're all used to talking about the kilowatt outputs of boilers and how many watts or kilowatts a radiator is. Now, technically, the calculation we're going to use is a volumetric flow rate and not a mass flow rate. And that's to do with the temperature of the water. But you'll hear us constantly refer to mass flow rate, and we should really be calling it volumetric flow rate because we're talking in litres per second. It's a minor faux pas, but for domestic, the difference between the mass and the volume is so small, and the quantities of water we're talking about are so small, it's not significant. But basically, 1 litre of water at 3.98 degrees centigrade and at 1013.25 hectopascals weighs 1 kilogram. So I think that's basically seen as 4 degrees centigrade at atmospheric pressure, that 1 kilogram of water, so 1 litre of water weighs 1 kilogram. But we're going to ignore that part of it. If you actually do a proper mass flow rate, it does take temperature into account. But say domestic, we're not so concerned about the very slight variations. So, right, back to the first explanation. So, energy equals joules, 1 joule per second equals a watt. Specific heat capacity. Now, specific heat capacity is the amount of energy it takes to raise 1 kilogram of a substance by 1 degree Kelvin, and 1 degree Kelvin is the same as as an index as 1 degree centigrade. Just the difference is the starting point. 0 degrees centigrade is the freezing temperature of water at atmospheric pressure, and 0 degrees Kelvin is absolute zero. But for 1 degree Kelvin, change of 1 degree Kelvin, it's also 1 degree centigrade. And I can't remember, absolute zero is minus 200 and something or other degrees centigrade. Can't remember the number. Okay, now water happens to be almost the perfect medium for transfer of heat. It has an exceptionally high specific heat capacity, and there are very few substances that carry a higher specific heat capacity than water. So it's extremely efficient at transferring heat energy. So to raise 1 kilogram of water by 1 degree Kelvin or 1 degree centigrade requires 4,182 joules of energy. And bear in mind that's energy and not power. If we were to transmit the heat into or out of that water in a period of 1 second, we would be consuming or delivering 4,182 joules in 1 second, and joules per second are watts. So we would be delivering, in effect, 4.182 kilowatts of power in the process of giving up that heat in 1 second. So I think you'll see the concept here. We've taken the energy, we've used the energy to raise the temperature of the water, and the speed at which we raise it is then determined in power. So if we had a so basically if we have a boiler, we're working usually on modern boilers at delta T20. So if we took 1 kilogram of water and we raised it by 20 degrees centigrade, we would have added 83,640 joules. And if we added that energy in 1 second or took it back away in 1 second, we would be talking of 83.64 kilowatts. So if you imagine an 83 or 84 kilowatt boiler, what we're talking about is being able to transfer or raise the temperature of 1 kilogram of water or 1 litre of water passing through that boiler in 1 second by 1 degree centigrade, 20 degrees centigrade. Right, so let's think about the time aspect then. If we want to work out the flow rates for transfer of energy in a heating system, obviously our flow rates contain the time factor. So if we talk in litres per second, we've got the volume, we've got the time, and also we've got the specific heat capacity, which contains the number of joules. So we have the 3 components to come up with our mass flow rate or our volumetric flow rate. So the formula basically is Watts divided by delta T times specific heat capacity equals litres per second. And this can be arranged in this very useful triangle here, a bit like the Ohm's law triangle. So Watts divided by delta T times specific heat capacity equals litres per second. And you can use that for transposition as well as the formula within that triangle, the same as you can with Ohm's law. So here for our example, we've got 1000 watts and we're dividing it by delta T20 times the specific heat capacity of water, which gives us 1000 divided by 83,640, which gives us a flow rate of 0.01196 litres per second. So that would be the expected flow rate if we wanted to deliver 1 kilowatt. So if you imagine having a radiator working at delta T20, if we wanted to deliver 1 kilowatt of energy for it, we would have to be able to measure the flow rate to that radiator at 0.01196 litres per second, which would be pretty difficult. Anyway, we tend to think in litres per minute when we're talking about flow rates, and a flow rate in litres per minute we achieve by multiplying by 60, and we come up with a flow rate of 0.717. But again, if you imagine trying to adjust a flow gauge or anything to 0.717 of a litre per minute, yeah, that's pretty damn accurate, really. We're lucky if we could work it out normally on a scale on an underfloor heating system, for instance. This kind of 0.5 and then 1, it's very hard to gauge these small flow rates between the two. So again, it's domestic and these accuracies are not critical. Understanding the theory is important, but the application maybe not quite as important as the understanding of the theory. Right, if you think in terms of a 30 kilowatt boiler then, rather than a 1 kilowatt radiator, we can actually use the kilowatt values by changing the joules to kilojoules. So we have 30 kilowatts divided by delta T20 multiplied by 32 kilojoules. And that conveniently, 42 kilojoules, by the way, is a rounding up of the 4182. So, which gives us this handy number of 84. 30 divided by 84 is 0.357 litres per second. And if we multiply that by 60 to get the flow per minute, we're talking about 21.43 litres per minute. So a bath tap is supposed to be commissioned at 18 litres a minute, to give you an example. So it might give you some kind of gauge. If you think of an old gravity tap flooding a bath, our flow rate will be slightly higher through a 30 kilowatt boiler at delta T20 than that bath tap filling the bath. 0.357 litres per second. Okay. So, and that's basically it. So, if you want to know how much energy you can transfer from one place to another, and you want to know what the flow rates are, you can calculate how much energy you want to get there, how much power you want to use at the destination. You can work out the flow rate required to deliver that energy to your radiator or your emitter using that volumetric or mass flow rate calculation. So I hope that's clear, and if it's not, just ask some questions.